In lesson 6.7, we'll be working with polynomial equations. We mainly are going to solve them, but we are going to learn some other properties about the roots that we have with polynomial equations. And right off the bat, we start with this very important theorem called the fundamental theorem of algebra. That says every polynomial equation of degree n has at least one complex root, and the corollary, or another theorem that's easily proved from this theorem, states that every polynomial equation of degree n, so degree n has exactly n complex roots, including multiple roots. So this is saying whatever our degree is, that's how many complex roots we'll have. And notice we're talking about complex numbers, so this could include imaginary numbers. And this includes multiple roots, and this means the same number, like 7, could be a root more than one time. So we don't just count that 7 once, we would count it all the times that it would be a root. So let's just jump right into these examples here. This first one says, state the number of complex roots and solve the polynomial equations. So as we look at this first one, we notice the degree of this is 3, which means that's how many complex roots there will be. So there'll be 3 complex roots. And then for factoring them, or for solving those equations, what we can do, we can either use what we learned with the rational root theorem and try to factor this using synthetic division, or what we can do is we also learned factoring by grouping, and we know that if we have a cubic function, that's one of the options that we could use. And looking at this one, I think this will be a good candidate for this. So I'm going to rewrite this. I'm going to go ahead and group the first 2 terms and group the second 2 terms. And over here, we have an x squared in common. What's left over is a 3x minus 1. And then here we can factor out a 9. And we have 3x minus 1. And remember, with factoring by grouping, what we do now is we look and we notice we have a 3x minus 1 in common, so that can be factored out. And what's left over? Well, this x squared plus 9 is left over. This is still equal to 0. And we remember, if we have things that multiply to equal 0, we can set them equal to 0. Now this one is close to being something that's familiar, but it is not. So here we can have 3x minus 1 equals 0. And x squared plus 9 equals 0. Add 1, divide by 3. So x equals 1/3. That's one solution. Over here we can subtract 9. Take the square root. When we take the square root of negative 9, we get square root of negative 9. We know we can't take the square root of a negative, so we know we have an I, and I should have put plus or minus here. X equals plus or minus the square root of 9 is 3, and we have I. So our solutions are x equals 1/3 and x equals plus or minus 3i. So we had 3 complex roots, and we found all 3 of those. So if we put 1/3 back in here and solved it, it would make it true, or if we put either of these 2 back in here and simplified it, would make it true. Coming over this next one, we have x cubed equals 5x minus 2. What we want to do is we want to get everything to one side. Well, first of all, we want to know the number of complex roots, and that's also 3, so we still have 3 complex roots. And then what we can do is we can solve this, and once I said it earlier, we want to get everything to one side. Subtract 5x and add 2 to both sides is equal to 0. Here we cannot do factoring by grouping So what we'll do is we have C. Our possibilities for C are plus or minus 1 and plus or minus 2. Our possibilities for D, which is the leading coefficient, is just plus or minus 1. Well, that's pretty easy. C over D then would be 1 over 1 and 2 over 1, so still just actually the same as C. So plus or minus 1, plus or minus 2, and so what we can do is we can use synthetic division and start trying these. So we have 1, x cubed, we have 0, x squared, so we're going to put a 0 in here. Negative 5 and 2. Let's try using 1, so we bring down our 1. I forgot I didn't show this shortcut method yet, but we bring down our 1, and then we do this. Still, we multiply, add. 1 times 1 is 1, plus 0 is 1. 1 times 1 is 1, plus negative 5 is negative 4. 1 times negative 4 is negative 4, plus 2 is negative 2. So that one does not work. Remember, we want to get a 0. Let's try negative 1. Again, we bring down our 1. Make sure when we do it this shortcut way that we're always looking back to our original equation. So negative 1 times 1 is negative 1, plus 0 is negative 1. Negative 1 times negative 1 is 1. So 1 plus negative 5 is negative 4. This would be positive 4, and this would give us a 6. All right, well, those two didn't work. Let's try 2. Bring down a 1. 2 times 1 is 2, plus 0 is 2. 4, or 2 times 2 is 4, plus negative 5 is negative 1. And 2 times negative 1 is negative 2, plus 2 is 0. And so 2 works, which means we're going to have to really squeeze this in here. X minus 2 is a factor. Our polynomial that's left over is x squared plus 2x minus 1. And this doesn't factor, but we could use the quadratic formula to solve this. So I rewrote our equation up here, and this doesn't factor, so we have to use the quadratic formula. So x equals, here's our b, so negative 2 plus or minus the square root of b squared. So 2 squared minus 4 times a times c, all over 2a, so 2 times 1. Simplifying this gives us negative 2 plus or minus. Well, what we have here is 4 plus 4, which is 8 over 2. We can simplify that square root of 8. That's a 2 root 2. And we notice we have a 2 in common in each of these factors, so this 2 can reduce. So this is a negative 1, this is a 1, and this is a 1. So we end up with x equals negative 1 plus or minus root 2. And so we have our 3 answers. So there's 2 of our answers, and then our other answer was 2. So here are the 3 complex zeros for this equation that we solved. The next one is actually x to the 4th power. So using x to the 4th power, we know that there's going to be 4 complex roots by the corollary of the fundamental theorem of calculus or algebra. And we can't factor by grouping, so we'll use synthetic division and the rational root theorem to help us. So our possibilities for C are the factors of 4, which are plus or minus 1. 2 is a factor of 4 and 4. And then our possibilities for D are the same things. And so C over D are all polynomial combinations we can make here. So 1 over 1, 2 over 1, 4 over 1, 2 over 1 we already have, 2 over 2 we already have, 2 over 4, which is half, and 4 over 1, 4 over 2, and 4 over 4. We have all of those already. I'm sorry, and I said these first ones wrong. I should be doing 1 over 1, 1 over 2, and 1 over 4. So I missed a 1/4 here. I'm having trouble. So plus or minus 1/4. I think that's all of our possibilities. I should have 1 over 1, 2 over 1, 4 over 1, 2 over 1, 1 over 2, 2 over 2, 2 over 4, 4 over 1, 4 over 2. Yeah. All right, now what we can do is we can try these. And we have 4, negative 16, 15, 4, and negative 4. We didn't have to fill any zeros in because we have each term represented. Let's go ahead and try 1. Bring down the 4. 4 times 4, 16, that's negative 12. 1 times negative 12 is negative 12, plus 15 is 3. 3 plus 4 is 7, and 1 times 7 plus 4, negative 4 is 3. Let's try 2. Bring down the 4. That's 8. 8 and negative 16 is negative 8. 2 times negative 8 is negative 16 plus 15 is negative 1. 2 times negative 1 is negative 2, plus 4 is 2, and 2 times 2 minus 4 is 0. So this works. So x minus 2 is one of our factors. And we're left with this polynomial. Now, what I want to teach you here, so we're going from an x to the 4th down to an x cubed, minus x plus 2. So don't keep going with this polynomial now. Now come to this cubic polynomial. So we have this cubic polynomial. We could keep using synthetic division, and what you would do is you would start over again. So you would take your coefficients, 4, negative 8, negative 1, and 2. And something else I want you to realize here is we can redo our rational roots. And also, since 1 did not work for this one, it will not work up here. So we can keep trying. We could try 2 again. So 1 didn't work, so it won't work. 2 did work. It could actually work again, but it might not. So it doesn't hurt to try. And I'm going to try it, but then I want to show you something else. Bring down the 4. 2 times 4 is 8. That makes 0. 2 times 0 plus negative 1 is 2. I'm sorry, 2 times 0 plus negative 1 is negative 1. 2 times negative 1 is negative 2 plus 2 is 0. So it actually worked again. I didn't realize that was going to happen, but it did. So now what we have, x minus 2 worked again. So we still have this x minus 2 from down here. We have another x minus 2 because 2 worked again. And then we have what's left over here. And so we factor this to this, and now we can solve. Now these are the same, so we only have to solve those once. So we know x equals 2. And what we do here, since it worked twice, what I do is I'll put multiplicity. Actually, I abbreviate multiplicity 2. And then we want to solve this one. Well, this is 4x squared minus 1 equals 0. We can add 1 to both sides. Divide by 4. take the square root, make sure we put plus or minus, so plus or minus, square root of 1/4 is the square root of 1 over square root of 4, which is 1/2. So our answer here is x equals 2, multiplicity 2, and then plus or minus 1/2. And so I know it looks like we have 3 answers. We have a 2, and then a 1/2 and a negative 1/2, but we have 4 because this 2 is worked as a root twice. There's 2 other theorems that we have here that kind of come together. There's the irrational root theorem and then the complex root theorem, and what it says is if a plus root b is a root, then its conjugate will also be a root. And that works for any complex number, any irrational number in this form. So it has to have a square root there. It can't be, this can't be like a 9 or something. And then same idea over here, except I didn't write this correctly. This would be a minus bi is also a root. And so that tells us, so in this example it says if 1 minus root 5 is a root, 3i is a root, and negative 4 plus 6i is a root. They're all roots with rational coefficients. What other roots must the polynomial have? Well, since 1 minus root 5 is a root, one of the other ones will be 1 plus root 5. Since 3i is a root, its conjugate of negative 3i is a root. And since negative 4 plus 6i is a root, negative 4 minus 6i is a root. So just by knowing these 3, we know 3 more, which means this actually will have a total, has to have a total of 6 roots. So this would be polynomial 6. Didn't ask that, but so if an irrational number in the form a plus root b or an imaginary number is a root, then their conjugates will also be roots. If a is a 0 of an equation, then x minus a is a factor, and the converse is also true. So we can actually write polynomial functions if we know some of the zeros. And so what we do here, if 3 is, 3 is a 0, so this means x minus 3 is one of our factors. This one gets a little tricky. If 1 minus 3 root 6 is a 0, then x minus that number, so minus, and then I put this in parentheses because that negative will get distributed, then this is a factor. So if we know zeros, we actually also know factors. Now we have to put one more here because 1 minus 3 root 6 is a 0, which means 1 plus 3 root 6 has to be a 0 also. And so another factor here, should have written this out better, is x minus this number. And so we could write a polynomial. Let's just write p of x for our polynomial equals x minus 3 times, we'll distribute our negative here, x minus 1 plus 3 root 6. I said 1, but I put an x, and then x, distribute this negative, x minus 1 minus 3 root 6. And then we can multiply these out. Would actually multiply the complex roots out first. Actually, it kind of works out nicely. Let's see here. If we do, well, we can just multiply them out. We got x times x is x squared minus x minus 3 root 6x. So that was just, those three came from distributing x. Now we distribute the negative 1, so minus x plus 1 plus 3 root 6. And now distributing the 3 root 6, we have plus 3 root 6x minus 3 root 6, running out of room here, and then minus, but just put it down here, 3 root 6 times 3 root 6 is 3 times 3 is 9, times 6 is 54. I'm not going to multiply in this x minus 3 yet. So as you see, the concept of making the polynomial isn't too bad. It's just a matter of multiplying things out. Makes it a little longer. So let's see, we have an x squared. We have a negative x, another negative x. So we have minus 2x. We have negative 3 root 6x and a positive 3 root 6x, which is 0. We already used this negative x. We have 3 root 6 and a negative 3 root 6. Those become 0, and 1 and negative 54 is negative 53. Well, that worked out nice. Doesn't have any irrational numbers in it. Now we can multiply this out. We get x cubed minus 2x squared minus 53x, and then distributing the negative 3 minus 3x squared plus 6x minus 159, plus 159. And then adding like terms, x cubed minus 5x squared minus 47x plus 159 is our polynomial function of least degree that has these number as the roots. Now when it says least degree, we went as low as possible. There were 3 zeros here. We could have added on another one. We could have put like x plus 7 or an x, and these things still would have been zeros. We just would have had extra, which would, having these would be x to the 5th, and so it said of least degree, so that means they don't want any extra zeros in there. And so there is our answer, and that is lesson 6.7, dealing with polynomial equations.